So let's talk about how to learn distributed systems. Now, the cool thing about distributed systems is that it's actually a study in systems and not in theory. But I really enjoy systems because when you come up with an idea, you can test it through experimentation. And as a matter of fact, most of distributed systems, the techniques used, have been discovered the hard way by looking at what works in the real world and trying it out, and when it doesn't work, trying something else. You learn distributed systems, and it was actually discovered by taking apart systems, by trying things, by debugging systems, by modifying existing systems and gradually improving them. And so hopefully these videos will help you learn from other people's experiences and what they've learned over the years by taking apart, debugging, and building distributed systems, so that you have a stronger foundation to build and discover more of the field for yourself, because it is an evolving science. So in these videos I'm going to cover a number of topics, and there's going to be actually more than one video per topic. And so right now I want to go through what some of those topics are, so you have a flavor of where you should go looking for other things to learn. The first topic I'm going to talk about is how distributed systems fail. Actually, not just how distributed systems fail, how individual systems fail. If you're going to build a system out of multiple computers, and you want that system to be more reliable than the individual computers, you have to really understand how will those computers break. Because if you don't know how computers break, it's hard to build a system that tolerates those breakages, that tolerates those failures, and keeps on working in spite of them. After we study that, we then need to talk about, well, if we're going to tolerate failure, we need a language to talk about that failure. Not only of the individual nodes, but of the entire systems. If I'm building a distributed system, there's going to be some users, hopefully, if it's a successful system, and those users will want to know, how reliable should I expect this to be? Now, you could invent your own language, often involving profanity to describe failures, but we have a common language that people tend to use instead. And they are, first, SLIs, which is a service level indicator. It's what you measure when you're looking at a system to understand how well it's performing and what it's doing. Once you have chosen a set of SLIs and come up with a technique for measuring them, you then want to develop your SLOs, which is how good do you want those SLIs to be? These are your goals. You might say an SLO is, I'm measuring whether my website can respond to browser requests or not, and I want it to respond to requests 99% of the time as measured over a 1-hour interval. Great, so that's your SLO. But from a customer's perspective, an SLO is meaningless unless you also know the consequences. And an SLA is an SLO plus consequences. So an SLA might be, I measure my website over a 1-hour interval, and I want it to be respond properly to browser requests 99% of the time. And if I fail to meet that, and you had a request coming in during that 1-hour interval, I will pay you as a customer $1 for your inconvenience. Now I've got a consequence. That motivates me to actually meet my SLO. And that's what an SLA is. And so SLAs typically form contracts, either written and formal contracts or informal contracts between a service provider and customers, or between teams in a larger company. Okay, so the next topic we're going to cover is the architecture of distributed systems, which are often designed around combining unreliable components to make a more reliable system. Because there's an infinite number of ways you can combine your components, but there are some common patterns, some common paradigms that people have found which tend to work rather well for combining components and building a reliable system. So we're going to talk about some of those. Now, you're building a system out of a series of nodes, and these nodes need to talk to each other. There really are two patterns which people have developed for having nodes talk to each other. One is a shared memory model, and we're really not going to talk about that because that isn't heavily used in the realm of distributed systems. We are going to talk about the message passing model, which is implemented in distributed systems using remote procedure calls, or RPCs. And so we're going to talk about both what RPCs are and how they tend to be implemented in order to perform well. Okay, so you've got a bunch of processes running on different machines, and they're trying to talk to each other, but they can't talk to each other unless they can find each other. And that's where the naming problem comes in. The naming problem is, how do you assign names to your processes and machines such that when the machines boot up and you want to start your distributed system running, they can find each other and talk to each other. Now, this sounds like it's just a simple problem. You just assign, this one's named Bob, this one's named Fred, this one's named Jane. Now they can talk to each other, right? But the names you choose can generate holy wars between developers because they express priorities about how do you expect these processes to be used? How do you expect them to interact with each other? How do you expect them to fail? And also, you can look at, well, okay, so you've got names. How do you find out what the names are? Once you start looking at the mechanisms used for sharing those names between nodes, you can get into some really complicated and interesting distributed systems problems. Next topic we're going to cover, time. Now, time is interesting because when you first think about time, you think you really understand time. I've got a watch. It measures time at 1 second per second. That's all you need to know, right? Well, not in a distributed system, because my watch isn't necessarily synchronized with your watch. So we may, at this moment in time, disagree about what time it is. Why does this matter? This matters whenever you have events happening on multiple machines and you care about the ordering between those events. If you have let's say you're implementing Facebook, and you have a popular Facebook posting, and people are commenting on it like crazy. The conversation would be disjointed if the comments appeared in one order as viewed by one user in Europe, and appeared in a different order as viewed by another user in North America. So you need the front ends, assuming there are different front ends in Europe and North America, to agree about what order the comments were put into the database on the different continents. So they need to agree about the time when those comments appeared. It becomes more critical in terms of the resolution you have to worry about when you're talking about things like stock transactions coming into a market, and you have to decide which sell order is matched up with which buy order and which transactions actually went through. Because stock traders really want things to go as fast as humanly possible, and they're also all building distributed systems. So you then say, okay, so we just need a really accurate way of synchronizing the clocks on the various computers. And that works as long as you can consistently set the clocks to be close enough to each other to have a much higher resolution on your computer's clocks and accuracy on your computer's clocks than the resolution of things you're trying to disambiguate. And it also requires that the error which you have is also smaller than the things you're trying to disambiguate. And that can get really, really hard when your distributed system is distributed over a long physical distance. Why can it get really hard? Because synchronizing clocks across multiple systems is limited, how accurately you can do that is limited by the amount of time it takes to communicate between those various systems. Basically your network round trip time. And so all I'm basically saying is that Einstein's theory of relativity starts to apply, and it can get really hard to get this right. And as a result, the theory folks in distributed systems have come up with some really cool ways of solving this problem where you just ignore wall time and instead you talk about the relationship between various events on the various machines. And this is a field, a subdomain called virtual clocks. And there are multiple ways of doing virtual clocks, and we're going to talk about that in a future video. So I was just talking about how you need your nodes to agree on the ordering of events. And this matters in many applications. But that sounds like consensus, the next line on my slide, right? Well, consensus is not only about agreeing on what happened. Consensus is saying not only do you need to agree on what happened, but no matter what happens, if any node fails at any time, if any network link fails at any time, if the system explodes and catches fire, and you bring the system back up, you still have to agree upon what happened. And so consensus algorithms attempt to not only agree upon an ordering between events, but also agree upon it in a durable way such that the ordering is written out to durable storage. There are two popular protocols in this area. The first one is Paxos, and this has been the gold standard for agreeing upon ordering, consensus, and making that ordering durable. Paxos is legendary for being hard to understand. So recently a competing protocol has been developed in academia called Raft, and Raft is, as far as we understand, as good as Paxos, but it's easier to understand. And so I'm going to talk a little bit about both of those protocols and how they work. The next topic we're going to talk about is distributed storage. If you have a lot of data, and face it, many distributed systems applications have huge volumes of data, you need to store it somewhere, and that's usually on disks or flash. And building a distributed storage system is fascinating, mostly because storage systems fail. And what I mean by this is the entire systems don't fail, but the components, rotating hard drives, are some of the most frequently failing pieces of a computer system. And as such, a lot of the areas where we discover how to tolerate failures get discovered first by the storage researchers. And so we're going to look at how some storage systems are designed in order to understand how to build some interesting examples of tolerating failure. After we study that, we're going to move on to security. Now, security is, like storage, an area where people can devote their entire careers to studying this. And so I'm not going to give you an entire career's worth of knowledge in one lecture. I don't have that much knowledge myself on this topic because this is not where I spent my entire career. But hopefully I can give you an introduction to some of the key areas you should watch out for when building and designing your distributed system, and who you should talk to get advice before you deploy a mission-critical distributed system. Next topic we're going to talk about is another area where people spend their entire careers on it, which is the art of operating a distributed system. This is, like all of the other fields in this series, an evolving field. It's actually one of the newest fields, which is how do you properly operate a truly huge distributed system. And it's a field that's being pioneered by large companies such as Google, Facebook, Twitter, and so on. And they're starting to write textbooks on the topic. Actually, the textbook that I've seen most recently is more a collection of essays. So it's still a really new field, and hopefully I can give you a brief introduction to it. Now, those are the topics we're going to cover. I want to tell you a little bit about this series of videos. I'm doing this as a supplement to a real class. And why do I say that? Because watching a series of videos on its own will not get you learning distributed systems. You need to actually get your hands dirty and build something. And so I encourage you to go and build something as you're watching these videos, or use these videos in addition to taking a class which has project work. I also want these videos to be a reference for when you get stuck. If you know sometime in the deep dark past you studied Paxos but you forgot it all because it's hard, hopefully you can come back and look at these videos and get a refresher and remember what you need to know in order to get your job done. I want these videos to be easy to use. I'm going to try and define terms as I use them, and that means you may see a bit of redundancy in things, but hopefully this makes it easier for you to use and easier for you to go through random access and just look at the topics that you care about in these videos. And the last thing I want to mention is that these videos are far from perfect. I know this because I'm not inside your brain. I don't know what you know, and I don't know whether I'm talking too fast, too slow, whether I'm covering the right topics or the wrong topics, whether I'm answering all of your questions. So I'd really appreciate it if you have any questions or concerns, or you want to change anything, or you just want to say how great these videos are. Yeah, right. Look down below. There are comments down below. Add your own comments below, and I promise I will do my best to read and respond to everything I have time to look at. So, thank you so much.